So what we're going to work with today is scientific notation and how to do operations with numbers in scientific notation. We're going to do a couple of things today. First of all, we're going to convert numbers between scientific notation and decimal notation. That's probably something that you've done either in a chemistry class or a math class, some other class somewhere along the way. We're going to review that. Decimal notation is also frequently referred to as floating point notation. If you've got a number in scientific notation, we're going to do the process for addition, subtraction, multiplication, and division for those numbers. We'll also deal with exponents, but how to deal with them if they are in scientific notation. And the third thing we want to accomplish is I want you to know how to do all these operations on your calculator. So I want you to know how to do them with your calculator, working them out by hand, and how to do the operations with scientific notation on your calculator without having to do them by hand. Those are the three things we want to accomplish. The principle that all of scientific notation is based on are powers of 10. A little bit of review from last week. First of all, if you see the value 10 to the third, that of course means 10 times 10 times 10. And if you see a value like 10 to the negative second power, that negative exponent represents reciprocals of 10. So it would be 1/10 times 1/10, or specifically, we're interested in that one on the far right, 0.1 times 0.1. That's the foundation that everything we're going to do is built on. Scientific notation is used to express really large or really small numbers, which show up frequently. If you're working in mechanical design or architectural technologies or the like, you're likely to deal with very, very large numbers. Forces, stress, strains in newtons or pounds. If you're working in electronics, you're more likely to deal with very, very small numbers like milliamps, microamps, microfarads, or even picofarads. Here's an example, 5.6 times 10 to the fourth. That's a very simple number that's written in scientific notation. A little bit of terminology. That 5.6 out in front, that's called the coefficient of this number. That's in scientific notation. Coefficient is a term that's kind of stolen from algebra, meaning a factor that's multiplied out in front, but 5.6 is called our coefficient. The 4, every number in scientific notation has the times 10 part in there, and the 4 is called your exponent or the power on 10. We say that formally the coefficient of a number written in scientific notation must always have an absolute value. That is, it could be negative, okay? We can't just say it's between 1 and 10 because that would exclude all the negative numbers. But its absolute value, which would include the negative numbers, has to be 1 or more, but it can't be 10 or larger. It has to be less than 10. 9.999, you might say. So here's an example. 8.52 times 10 to the 6th is written in scientific notation. Now I said that there were two criteria. The second one goes without saying. The second criteria is that that power of 10, in this case it's a 6, it has to be an integer. Okay, we couldn't write a decimal value in that exponent, but that one usually is assumed to be true anyway. These two numbers are not in scientific notation. 85.2 times 10 to the 5th. What's wrong with 85.2 times 10 to the 5th? The coefficient is too large. And the second one, 0.852 times 10 to the 5th. That one's not in scientific notation because? The coefficient's too small. So that settles that. What we're going to do now is we're going to take some values, both large and small, and we're going to put them into scientific notation, and then we'll take some scientific notation values and write them in floating point or decimal form. Here's the first example. We want to write the number 494,200,000 using scientific notation. Now, we won't go through this long explanation every time. But first of all, don't you agree that 494,200,000 is the same as saying if we were to take and divide this by 1,000, or better yet, 1,000,000, or better yet, 100 million, we can write this as 4.942 times 1. And we moved it 1, 2, 3, 4, 5, 6, 7, 8 places, so we're going to say that this has 8 zeros on it. Everybody agree that that statement's true? Okay? Sure it is. Well, the idea of scientific notation is that you're taking all these zeros, all these factors of 10, and compressing them into a power of 10. And so we would write this as 4.942 times 10 to the 8th power. That exponent always indicates how many places you have to move your decimal point. Now, was there another option? I chose to make this 4.942 times 10 to the 8th. Is there any other options? Could we write it in scientific notation a different way? In other words, could you land that decimal place in a different spot and have a different power of 10? No. Why? It wouldn't be between 1 and 10. If you go way out here, you'd end up with 0.494. That's too small. If you put the decimal point right there, we'd get 49.4. That's too big. There's only one option. 4.942 times 10 to the 8th is the value in scientific notation. 59,000 using scientific notation. Now, we won't factor out all those zeros this time. We'll just count how many decimal places we need to move it, and we'll call it 5.9 times 10 to the what? 4th power. Had to move it 4 spots. Okay? Now, we want to write the number 0.000371 using scientific notation. Some minor point about notation that you may or may not have seen before. When we're dealing with large numbers, we put a comma every 3 zeros to make it easier to read. You don't use commas on small numbers. Instead, you put a little extra space every 3 numbers, and that makes it easier to read and not miscount decimal places. So it's the same principle, but use a space instead of a comma. So 0.000371 using scientific notation. First of all, we're going to move that decimal place over until our coefficient is between 1 and 10, and that turns out to be 3.71 times 10 to the... Now, are we actually multiplying this number by 10 to move the decimal point over? No, you're actually multiplying it by 10 to the negative 1, or 0.1. So what we have to represent up here is the fact that we moved it 4 places, but since it's actually a very small number, we make that exponent negative. 3.71 times 0.1 to the 4th power would give us that original value. One more quick one. 0.099. 0.099 is going to be what when we put it in scientific notation? 9.9 times 10 to the negative 2nd power, negative 2. 9.9 times 10 to the negative 2. Questions about any of those three? Okay. Well, in general, large numeric values are expressed using positive powers of 10. If you've gone through scientific notation before, sometimes there's left and right, move the decimal point left or right according to the sign. That's fine. I have trouble with that. I just remember that positive exponents of 10 represent large numbers, so I have to move the decimal in a direction that makes it large. And very small values, values less than 1, are represented by negative powers of 10. That's an easier way to keep track of where you're moving the decimal point. Now what we're going to do is we're going to take some numbers that start out in scientific notation and write them in floating point notation. Once we're done with a couple of examples of that, then we're going to move on to do the operations. Let's write 5.90 times 10 to the 7th using decimal, or again, that's often called floating point notation. Well, you see a positive exponent on 10. Does that mean you're going to write a large number or a small number? It's going to be a large number. We're going to move it 7 places. We want to make it larger, so it's going to have to be to the right. And so we end up with 5, 9, 2 places gets it out after the 0. And now we have to put on how many more zeros here? We have to put 5 more zeros. We can move it 1, 2, and then we need to move it 5 more places. We can put in our commas appropriately, 1, 2, 3, 4, 5, 6, and as it turns out, 5.90 times 10 to the 7th is actually equal to 59 million. Look okay? Another. 9.004 times 10 to the negative 8 using decimal notation. Well, negative exponent must be a small number. We're going to have to move that decimal point in such a way that the number is very small, that it's going to have to be to the left. We can move it 1 spot to get it in front of the 9, and then we're going to have to put 7 more zeros in front of that. So 1, 2, 3, 4, 5, 6, 7. There's our 7 zeros. And then 9, 0, 0, 4. 0.00000009004. This number is equivalent to what? 1.560. No need to move the decimal point. 10 to the 0 means you're multiplying it by 10 to the 0th power, which is actually, what's every number to the 0th power? We haven't mentioned this yet. 1. Any number to the 0th power is 1, so it's just 1.560. And last one, 2.4 times 10 to the negative 1 power. .4 times 10 to the negative 1 power becomes 1 spot. It's got to get smaller. 0.24. Now, I know you're wondering, what are you wondering? In the back of your mind, you're all wondering. Exactly. You're all wondering, how are significant digits handled? Well, in general, and we're going to dismiss this rule as soon as we see this screen. The general rule is that significant digits are always contained in the coefficient. Okay? So for example, if we go back up here for a minute, 5.90 times 10 to the 7th, how many sig digs have you got there? 3. And so this number should be expressed as 59 with a line over that 0 to show that that is to the nearest 100 thousandths. 9.004 contains 4 significant digits, but that's reflected in this decimal number. That has 4 significant digits. 1.560, 4 sig digs, 4 sig digs here. 2.4 times 10 to the negative 1, 0.24. Here they both have 2 sig digs. So it's really not much of an issue. If there's any question, we have a number in scientific notation, all the sig digs are in the coefficient. 5.90 times 10 to the 7th does have 3 significant digits. Okay. So we can go into and out of scientific notation. What we're going to spend the rest of the time on are the operations, how to add, subtract, multiply, and divide numbers that are in scientific notation. Questions up to this point, or does that look good? Good. Hopefully that was mostly review to you, just a matter of getting brushed up. Okay, we're going to start with addition and subtraction. Numbers that are written in numbers that are written with the same power of 10. That's good news. We can add or subtract them if they have the same power of 10. If they don't have the same power of 10, we have to tweak them so that they do have the same power of 10 before we can add or subtract them. Here's an example. We want to take 4.89 times 10 to the negative 6th power and add to it 1.35 times 10 to the negative 6th power. Now I want you to notice something. This won't be on the PowerPoint slide there, but I'm going to change the way it's written up here on the board. Very subtle change. I'm going to get rid of those parentheses for a minute. I'll put them back. Don't bother putting this in your notes, but just think about it. If I don't have those parentheses in there, does it change the nature of the problem? Does that change the problem? No. It doesn't. Why doesn't that change the nature of the problem? Drew? Exactly. You would treat this multiplication and this multiplication, you would do those first anyway. So this gets computed and that gets computed before you add them up anyway. So that's right. Now usually numbers, or often, numbers that are in scientific notation are enclosed in parentheses, and that's just so that when you glance at them with your eye, your brain registers and picks them out a little bit easier. And that's what we'll typically do, and your book usually does too. So to add these up, we have to look. First check is, do the powers of 10 match? Yes, they do. So all we need to do is add the coefficients. 4.89 plus 1.35. And if you add 4.89 and 1.35, you get 6.24. That's our new coefficient. And the power of 10, what do you suppose happens there? Stays the same. Okay? So these two added together become 6.24 times 10 to the negative 6. The powers of 10 matched. We add the coefficients and preserve the same power of 10. That's what you hope for. You hope that the powers of 10 are the same. Unfortunately, they often are not. One more quick example. 9.66 times 10 to the 4th. Powers of 10 match. Go ahead and add the coefficients. If you add those coefficients, you end up with what? 16.98 times 10 to the 4th. Okay? Now, is that in scientific notation? It's not. Why not? It's too large. Now, I have one word for you. This is a little bit corny. I realize this is corny, but it works. Think seesaw. All right? Whenever you've got to adjust where this decimal point is, or if you have to adjust what you want your power of 10 to be, which we'll see in a minute why you need to do that, you always think of these two parts of the number as being a seesaw. If one side gets lower, the other side has to get larger. And if one side gets larger, the other side has to get smaller, and vice versa. So if we take 16.98, do we have to make that coefficient larger or smaller by a decimal place? It has to become smaller. That means that this is going to become 1.698. What does that do to your power of 10? It sends it up. This went down, this side has to go up. What we're really doing is we're taking a factor of 10 and slipping it over to here. So the correct answer is 1.698 times 10 to the 5th. 16.98 times 10 to the 4th is the right value, but it's not in scientific notation. All right, well, first thing you check is, do your powers of 10 match when adding or subtracting? And unfortunately, they do not. You need to make them match. We need to either make this power of 10 into a 6, or we need to make this one into a 7. And ultimately, it does not matter which one you choose. Now, you'll find from experience that there's a choice that's better to make, but ultimately, it doesn't matter. Okay? So let's just do this one. Should we change the 7 power to a 6, or should we change the 6 to a 7? Let's change the 6 to a 7. Completely arbitrary choice. So this one's going to remain the same. This will stay 4.05 times 10 to the 7th power. To that, we're going to add, okay, we need to tweak this. This is going to become times 10 to the 7th. What are we doing with that power of 10? It's going up. So what happens to happen to the coefficient? It's got to get smaller. So that becomes 0.332 times 10 to the 7th. Everybody agree with that? Now the powers of 10 match. We can go ahead and add them together. 4.05 plus 0.332 becomes 4.382. And your power of 10 is 7. Now you could ask the question, and it would be fair. Well, wait a minute here. We're adding hundredths to thousandths. Shouldn't we be limited to the nearest hundredth here? You got 2 decimals here and 3 here, so what's the most you could keep? Just the hundredths. You should be limited to 4.38 here. And if we were following strict sig-dig rules, that is exactly what we do. We'd call it 4.38 times 10 to the 7th. However, your book and most practical purposes treat these as semi-exact values. That is to say, we just add them and we keep all the significant digits. So for the sake of what we're doing today, we're just going to stick with that. When you do all your homework, just treat them as exact values, okay? Otherwise, every answer you get will disagree with the back of the book. That's going to be a hassle. All right. Now, from the last example, did anybody spot? I said you can change unmatching powers of 10. You can change either one. You can change that to negative 11 or this to negative 13. But there's one way that will usually work a little bit better. Did anybody think ahead and see what that way is?
I changed the one from a negative 11.
You change this to a negative 13? Okay. Well, let's do that. Let's change. I'll let you think about it. We're going to do the other one, we're going to do this one a little bit differently. Same principle. The last one we changed 6 to a 7. This one, let's change that negative 11 to negative 13. Again, an arbitrary choice. In this example, it's going to work out differently, though, and I want you to watch what happens. It'll still be okay, but I want you to think carefully about this problem. Let's change this one to negative 13. So this number will stay the same, 7.54 times 10 to the negative 13th. This one will become, okay, this is going to be times 10 to the negative 13th. Now, what does this number become? $690.6. I wish you could have just seen some of the expressions I just got. Think carefully about it. Are you making this number larger or smaller? You're making it smaller. And so this number has to get bigger. With negative numbers, it seems backwards. Negative 11 has to get smaller to become negative 13. Does that make sense? And so this has to become 690.6 times 10 to the negative 13th. That's where almost all mistakes in scientific notation are made, are in moving the decimal the wrong way when dealing with negative powers of 10. Well, now we can proceed. 7.54 times 10 to the negative 13th plus 690.6 times 10 to the negative 13th gives you 698, yeah, 0.14? 14 times 10 to the negative 13th. 698.14 times 10 to the negative 13th. Okay, we got our sum, but the problem is it's not in scientific notation, and so we have to modify this a little bit. We have to change this to our final answer. We need to get that down to 6.9814. Times 10 to the, now we made this side smaller, so this side has to get bigger, and it becomes negative 11. We should have changed it to negative 11. Exactly. Grant's right. We should have changed it to negative 11 because if we would have, we wouldn't have had to have done this last step. Now, do you see what to watch for? We could have done it either way, but what are you watching for on those powers of 10? You should always change it to the one that is greater. Exactly. You don't have to, but if you do, it'll save you this last step. If you change unmatched ones to the greater power of 10, it will usually end up in scientific notation, and you won't have to move that decimal at the end. Okay, we want to subtract this time. Now the subtraction sign, everything we're going to do is exactly the same. It's just that we'll subtract the coefficient. So we're doing addition and subtraction at the same time here. powers of 10 do not match. What do you want to switch? Do you want to switch the 10 to the negative 8th to 10 to the negative 7th, or negative 7 up to negative 8th? Excuse me, down to negative 8th. Let's make them negative 7. That's the greater of the two, and so we should avoid that last step of putting it into scientific notation. So this one has to become 10 to the negative 7th. That'll make the coefficient what? What is it? 0.955. Because we're making the power of 10 larger, the coefficient must get smaller. 0.955 times 10 to the negative 7th minus 5.05 times 10 to the negative 7th. Our powers of 10 now match. We can perform that subtraction. 0.955 minus 5.05 should get negative 4.095. Better be a negative number. 0.9 something minus 5 point something. That's got to be negative. And then our power of 10 is negative 7. And we're done. The absolute value of the coefficient is between 1 and 10, and so we can leave it just the way it is. Look okay? Okay, now we're going to rework this problem, but I want you to do it on your calculator. Thing to watch for, calculator. There's a lot of variation in how calculators do everything we're doing for the next 2 or 3 days here. But most calculators have one of 3 keys for entering scientific notation. It's either EE, and if you have a Texas Instruments like I do, it's EE. Even most graphing calculators have the EE button. Or you might have EXP. I think Casios often have EXP on them. Sharp does too. Or maybe it's Sharp that I'm thinking of. Well, EXP. Or some of them have this times 10 to the x key. They all mean the same thing. They all mean times 10 to some power. So that button that we just found packages multiplication and the base of 10 all into one key. You do not ever need to type times 10 when you're using your calculator in scientific notation. That key does it every time. So rework this problem on your calculator. Keystrokes carefully. This is the same problem we just did, incidentally. Okay. Now, the first thing is we're going to start with that 9.55 times 10 negative 8th. You're going to enter 9.55. Now, you do not type times 10. If you do, your answer will be wrong every time because you're introducing an extra decimal place in there that you don't want. 9.55, hit the EE or EXP or times 10 button, and then type your exponent of negative 8. Some calculators, you have to put the negative sign in after the 8. Okay? And I won't even attempt to draw what the display looks like because they're all different. Then you're going to subtract and then type the second value, 5.05 EE, EXP, or times 10 to the x, and an exponent of negative 7. And your calculator should produce negative 4.095 times 10 negative 7. How many of you got the same result? Good. How many of you have a bunch of zeros because it put it in floating point notation? Yeah. If you got a bunch of zeros, you need to ask your calculator to put it in scientific form. And that's done by finding the mode key of your calculator. Let's take just a minute. I want you to do this one. I'm going to give you a hand if you're not getting it. But to wrap this up, multiplication and division. When you're multiplying, the powers of 10 do not have to match, but you have to recognize this fact about exponents. If you're going to multiply 2 powers of 10 together, your product will have the sum of the individual exponents. For example, the one that's shown here, 10 to the 3rd times 10 to the 4th power equals 10 to the 7th. Here's why. You don't have to put this in your notes, but you have to understand the principle. The reason that that works is if you take 10 times 10 times 10, that's 10 to the 3rd, right? And we're going to multiply that by 10 to the 4th, which is 10 times 10 times 10 times 10. How many powers of 10 have you actually got? 7. 10 to the third times 10 to the fourth is 10 to the seventh. In general, you could say that some base with, let me say that differently. You could say that 10 to some power plus 10, times 10 to another power, I'm having a hard time writing, 10 to another power is equal to 10 to the sum of those two powers. Principle makes sense? If you understand that, then you know how to multiply numbers that are in scientific notation. Here's an example. We're going to take 4.7 times 10 to the third times 1.3 times 10 to the ninth. Well, to multiply powers of 10, multiply numbers in scientific notation, we multiply the coefficients first. 4.7 times 1.3 will give us our new coefficient. And that's 6.11. Times, now, this is the rule that we just saw. If you take 10 to the third and multiply it by 10 to the ninth, you're left with 10 to the 12th power. Is that number in scientific notation? You're done. The powers of 10 don't have to match, but the likelihood of getting a product here that's larger than 10 is very high. So you will frequently have to take this coefficient and change it so that it's between 1 and 10. In this example, it worked out nicely. Another one with negative exponents, 6.5 times 10 to the negative 8th. Times 2.8 times 10 to the negative 12th power. Multiply those coefficients, 6.5 times 2.8, we get a new coefficient of 18.2. Times 10, and what will be our power on 10? What is it? Negative 20, that's right. Negative 8 plus negative 12 is negative 20. That's the product, but it's not in scientific notation, so we got to tweak that. We end up with 1.82 times 10 to the, and now what's our new power of 10? Exactly. This side gets smaller, this side's going to get larger, and the next number larger than negative 20, the next integer is negative 19. That number's in scientific notation. Well, division follows the very same principle. When two powers of 10 are divided, we subtract the second exponent from the first. Again, why does that work? Because if we take 10 to the 7th, for example, and divide it by 10 squared, or 10 times 10, what happens to some of those 10s? They cancel. A pair of them cancels. Every one on the bottom cancels with one of the 10s on the top, and we're left with how many of them? 7 minus those 2, we get 10 to the 5th power. That's the reason that when we divide powers of 10, the exponents are subtracted. Okay, and so let's wrap this up. A couple example problems. Let's take 9.1 times 10 to the 15th divided by 2.6 times 10 to the 6th. Divide your coefficients. 9.1 divided by 2.6 gives you a result of 3.5. What's our power of 10 going to be? 10 to the 15th minus, 15 minus 6 gives us 10 to the 9th. That's right. 3.5 times 10 to the 9th is the correct value. And again, you could perform that on your calculator by entering the numbers in scientific notation. We won't take the time to do that now. And here's our last problem. Now, here's a case where when you divide those coefficients, it's not going to work out evenly. And so, since it's not working out evenly, we are going to have to cut it off somewhere. And so then we revert back to our significant digit rules. So 6.571, and we're dividing that by 4.113, you end up with 1.5976173 and so on. How many sig digs should we keep here? Let's keep 4 and call it 1.598. Times 10 to the... Now, careful, this is a very common place to make a mistake. What is your exponent on 10? I heard a couple different answers. I heard 4, I heard 1, I heard 7, or maybe negative 7. It is 1. Why is it 1? Because we take negative 3 and subtract off, because we're dividing, negative 4. And so negative 3 minus a negative 4 is negative 3 plus 4. Our power of 10 is 1. And that is where we're going to stop for today.